All right, so today we're going to spend our time going through the content of chapter 14, dealing with the last of the basic organic functional groups, carboxylic acids, esters, amines, and amides. And we'll really spend some time going through some of the reactions and such like that by doing some problem solving. So we'll start by taking a look at question 14.62. Right? And it's really all about drawing the products of the reactions. So let's start with the first one, letter A. So essentially, to be successful with this, you have to be able to do a couple things. You have to be able to recognize the reaction that's going to occur, and then be able to essentially come up with the product of it. So when I see this, I see a carboxylic acid plus sodium hydroxide. So the combination of that reminds me that I'm dealing with a carboxylic acid salt. So essentially, how do I come up with the product? Well, for me, a couple things. Carboxylic acids are acidic, and they fit the Arrhenius definition of dissociation. And essentially, where does a carboxylic acid dissociate? It dissociates between the O and the H of the carboxyl group. And essentially, the carboxyl group is going to come off as H+. Now, sodium hydroxide is a strong base. So I like to think of sodium hydroxide in these reactions not as NaOH, but as Na+ and OH-. Now, essentially, the H+ and the OH- are going to combine to give you water. So water is going to be the byproduct of the reaction. For the carboxylic acid, everything stays the same until you get to the carboxyl group. But now, instead of having the C double bond O connected to OH, instead, the C double bond O carbon is going to be connected to an O-, which essentially is your carboxylate ion, C double bond O connected to O-. Now, what else is present that's going to be attracted to that O-? It's going to be Na+. And what type of compound is this? This is a carboxylic acid salt. And the type of bond that you have between the O- and the Na+ is an ionic bond, because in a carboxylic acid salt, just like salts in general, you have cations and you have anions that are attracted by an ionic bond. And in essence, if you were really to draw a dash between the O- and the Na+, that would really technically be incorrect. So when you have a carboxylic acid plus sodium hydroxide or even potassium hydroxide, the product is going to be a carboxylic acid salt. All right. Letter B. So for letter B, we have the following carboxylic acid. And in this case, we have reaction with water. So, as you mentioned in the previous example, and as their name implies, carboxylic acids are acidic. And again, a carboxylic acid, when you place it in water, and even in the other example, sodium hydroxide, you're using a sodium hydroxide solution, which, as we know, base solutions are aqueous solutions. So the product would be essentially, the solvent's going to be water. So that's why we consider the carboxylic acid to sort of dissociate as well. So again, the bond, where carboxylic acid dissociates is between the O and the H. And the H is going to come off as H+. Now, in just water itself, that proton is going to be picked up by the water. So the H2O becomes H3O+. And what happens to the carboxylic acid? The carboxylic acid is going to become its conjugate base, which is the carboxylate ion. So everything else would stay the same until I get to the C double bond O carbon. But now, instead of that C double bond O carbon being connected to OH, instead, that C double bond O carbon is going to be connected to what? O-. And in this example here, this is the carboxylate ion that would be generated in water. Right, letter C. So here we have another carboxylic acid. This time we're reacting it with an alcohol. All right, they give double arrows. Not really a big deal. H plus in heat, not really so much involved. The big thing is carboxylic acid plus alcohol. You have to remember what reaction it's going to be. Carboxylic acid plus alcohol is essentially going to be esterification. Okay. Essentially, it's the main way to come up with an ester. From my perspective, how do you come up with the ester product? The way that you come up with the ester product, just write that a little bit clearer. The way you come up with the ester product is the following. You go to the carboxylic acid, and from the carboxylic acid, you take off the OH. Then you go to the alcohol, and from the alcohol oxygen, you take off the hydrogen. So the byproduct of this reaction is going to be water. The OH and H essentially combine to give you water. The bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the alcohol oxygen. I like to start by redrawing the carboxylic acid portion first. And everything's going to stay the same until you get to the C double bond O carbon. And it's at that point that you are going to have your connectivity to the alcohol oxygen. So this bond right here is the linkage between the C double bond O carbon and the alcohol oxygen. And then in this case, what is still left attached to the alcohol oxygen that has to be filled in? The alcohol oxygen is attached to a CH3. And right over here, when you have C double bond O connected to oxygen, and the C double bond O carbon is singly bonded to oxygen, which is singly bonded to carbon, what type of functionality is that? That, of course, is your ester functional group. So carboxylic acid plus alcohol is essentially what is known as an esterification reaction. Letter D. So here we have another carboxylic acid. This time we're reacting it with aniline. So carboxylic acid, aniline is an example of a primary amine. What type of compound do you get when you react a carboxylic acid with a primary amine? You're going to get an amide. So the type of functionality that's going to result is that you're going to get an amide. And we know for amides that the C double bond O carbon is going to be connected to a nitrogen group. So how do we come up with the amide? Well, first off, we're going to go to the carboxylic acid. And again, from the carboxylic acid, we're going to take off the OH. Now we're going to go to the nitrogen of the amine, the aniline in this case. And from that nitrogen, we're going to take off one of the hydrogens. So again, the byproduct of this reaction is going to be water. The OH and the H essentially combine to give you water. The bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the nitrogen of the amine. Again, I like to start by drawing the carboxylic acid portion first. Everything's going to stay the same until I get to the C double bond O carbon. And now I have my connectivity to the nitrogen of the amine. Now, in this case, when I take one of those hydrogens off, there's still one hydrogen on that nitrogen. And that nitrogen is still connected to a benzene ring. And what type of functionality do you have? Because the C double bond O carbon is connected to nitrogen, you have an amide group. So carboxylic acids plus either ammonia, primary amines, or secondary amines are going to give you amides. The reason why tertiary amines can't be used is that for a tertiary amine, you have, well, in this reaction, you have to take a hydrogen off the nitrogen in order for the reaction to occur. Remember, your tertiary amines do not have any hydrogens on the nitrogen. There are 3 carbon groups directly connected to the nitrogen. All right. So let's jump to 1464. All right, let's take a look at letter A. So here, let's draw the structure. So we have an ester, and we're going to react it with sodium hydroxide. C double bond O, OC is going to give her an S and ester group. So again, it's about recalling and then being able to sort of understand and draw out what's going to happen. So first off, when you have an ester with base, we're talking about, essentially base hydrolysis of the ester. What are the products of base hydrolysis of the ester? You get a carboxylic acid salt and an alcohol. So those are the two products of ester-based hydrolysis. Now, this is sort of my suggestion about how to come up with that. Couple things. When I talk about esters, for me, esters have a key bond. That's the bond that forms when esters are made by esterification. And whether it's acid hydrolysis or base hydrolysis, that's the bond that breaks when esters split apart. What bond is that? It's the single bond between the C double bond O carbon and the oxygen, which actually should be commonly referred to, and I commonly refer to it as the alcohol oxygen. Because if you look at esterification, that portion comes from the alcohol that could be used to make that ester. Okay. The other thing I would do here, and we talked about this before, is I wouldn't think about the NaOH as NaOH. I would think about it as Na plus and OH minus. Now, the interesting part about this reaction is that initially, the OH group of the base takes the place of the alcohol part of the ester. To give you what? To give you a carboxylic acid. So in this case, if the, and let me just use a couple different colors here to sort of highlight. I'm just going to draw the sodium hydroxide in a different color. So in this case, if the OH group of the base were to take the place of the alcohol part of the ester, the carboxylic acid we initially get would be the following. This part comes off, CH3, CH2, C double bond O, OH. Why isn't a carboxylic acid one of the final products here? And this is just basic acid-base chemistry. We are under basic conditions. Can you have an acid under basic conditions? And the answer is no. As we saw earlier, what happens to a carboxylic acid under basic conditions? It becomes a carboxylic acid salt. Now, in this case, what I would say is that essentially the alcohol oxygen ends up picking up the hydrogen from the carboxylic acid. So the alcohol product here you'll have the alcohol portion. And then that alcohol oxygen picks up the hydrogen from here. Because remember, that's the acidic portion of a carboxylic acid. What part of a carboxylic acid is lost under basic conditions? It's going to be the hydrogen of the carboxyl group. Here, it's going to be picked up by the alcohol oxygen. Then, what happens to the carboxylic acid? Everything stays the same, but now instead of having C double bond O connected to OH, instead, and we saw this earlier as well, you're going to have C double bond O connected to what? O minus. And then what else is present that's going to be attracted to that O minus charge? Na plus. And what type of compound is that? That is a carboxylic acid salt. Okay. All right. Let's go to letter B. So here we have the following structure. It's H2O, and then we've got H plus and heat. All right. So what do we got going on here? Well, again, we have an ester. We have water, H plus, generic symbol for acid, heat. So what do we got here for the ester? We've got acid hydrolysis. So what are the products of acid hydrolysis? It's a carboxylic acid and an alcohol. A couple things for me in terms of drawing the product. First off, where does the ester split apart? The ester splits apart between the C double bond O carbon and the alcohol oxygen. I should have mentioned it earlier, but what you need to be able to tell is which part of the, in terms of that squiggly line, to the left or to the right, is going to be the carboxylic acid or the alcohol portion. The easiest way to tell is the C double bond O group has to be the carboxylic acid portion. Alcohols don't have C double bond O groups. So the C double bond O group has to come from the carboxylic acid. Because esters can be written with the single bond oxygen to the left or to the right of the C double bond O carbon. So you have to be mindful and be able to really figure that out. So in this case, the carboxylic acid portion is to the left, the alcohol portion is to the right. You had the same thing in the other example. Now, the other thing I think would help drawing the products here is don't think about the water as water. Think about it as H bonded to OH. So what happens? The alcohol oxygen ends up picking a hydrogen up from water. So what does that lead us to? Well, it leads us to our alcohol product, which in this case is 1, 2, 3, and then O, and then we're going to pick up that hydrogen to give us OH. So that would be our alcohol product. And then the C double bond O carbon is going to pick up the OH from water to lead us to what? To lead us to the carboxylic acid. So I'd have CH3, CH with another CH3, C double bond O, and then that C double bond O carbon is going to be connected to what? That C double bond O carbon is going to be connected to OH. What type of structure is that? That, of course, is a carboxylic acid. So that's my recommendation for drawing the products of that reaction. Letter C. So here we have CH3, CH2, C double bond O, NH2, plus NaOH, and heat. All right. So first off, what type of organic compound do we have here? We have an amide. Reaction with sodium hydroxide is going to be base hydrolysis for the amide. So what's the products of base hydrolysis for an amide? It's a carboxylic acid salt and either ammonia or an amine. Now, in terms of how to come up with the ammonia or the amine, it's the same way. The difference basically is based on the type of amide that you start with. Here, we have a primary amide. How do I know that? Because besides the bond to the C double bond O carbon, the nitrogen has 2 other hydrogens attached to it. That would make a primary amide. If the and that is actually, you'll see in a moment, that's going to lead us to ammonia as the nitrogen product. If you had a secondary or tertiary amide, so for a secondary amide, the nitrogen would have, and again, this is besides the bond to the C double bond O carbon, it would have 1 hydrogen and 1 carbon group. And if it was a tertiary amide, it would have 2 other carbon groups attached to it. Couple things to get started. Just like for esters, when I talk about the key bond or key bond, I consider there to be a key bond for amides as well. And that's the single bond between the C double bond O carbon and the nitrogen. Because as you saw earlier in this example here, that's the bond that forms when amides are made. And essentially that's the bond that's going to split when amides are, that's the bond that's going to break when amides are split apart. And then the other thing is, again, I'm going to not think about NaOH as NaOH. I'm going to think about it as Na plus and OH minus. Now, similar to ester-based hydrolysis, this reaction is also going to initially generate a carboxylic acid. What's going to happen here is that the OH group of the base is going to take the place of the nitrogen part of the amide. So the carboxylic acid that I initially get in this example is propanoic acid. Now again, why isn't the carboxylic acid one of the final products here? The reason why it's not one of the final products is because we're under basic conditions. As we talked about earlier, and we'll mention again here, what part of a carboxylic acid is lost under basic conditions? It's the hydrogen of the carboxylic acid. In this reaction, that hydrogen is going to be picked up by the nitrogen. So in this example, the nitrogen product, the NH2 becomes NH3. And what compound is that? That, of course, is ammonia. So our primary amide has led to ammonia as the nitrogen product. Now, again, what happens to the carboxylic acid? Everything stays the same until you get to the C double bond O carbon. But now instead of the C double bond O carbon being attached to OH, instead, it's going to be attached to O minus. And what else is present that's going to be attracted to that O minus? Na plus. And as we saw earlier, what type of compound is that? That, of course, is a carboxylic acid. Sorry, that, of course, is a carboxylic acid salt, not a carboxylic acid. Okay. All right. Let's go to 1470. So here's letter A. So here we have an amine plus water. Okay. So, as you know, amines are derivatives of ammonia, where you take out one or more of the hydrogens and replace them with carbon groups. As you also know from the acid-base chapter, ammonia is a base, not according to the Arrhenius definition, but according to the Bronsted-Lowry definition of being a proton acceptor. Well, similar to ammonia, amines are proton acceptors and will do so when you take one and place it in water. So what happens is the water is going to donate a proton to the nitrogen of the amine. When the water does that, what does the water become? Well, if water is the acid, it's going to become its conjugate base, which is OH minus. For the amine, everything stays the same, but now the nitrogen picks up an additional hydrogen. Now, one of the other big changes is that when nitrogen has 3 bonds, nitrogen is neutral. But when nitrogen has 4 bonds, it has a +1 charge. In a sense similar to oxygen, when oxygen has 2 bonds, oxygen is neutral. When oxygen has 1 bond, it has a negative charge. So the nitrogen protonates and goes from 3 bonds to 4 and now has a positive charge. Now for letter B, we're going to take the same amine, but now we're going to react it with hydrochloric acid. Okay. Now I didn't mention it before, but I'll mention it here. When we talked about the reaction of the carboxylic acid plus sodium hydroxide, back when we started our discussions this evening, the first reaction we did, that was an example of a neutralization reaction. Acid plus base giving you salt and water. That's an example of a neutralization reaction. This is essentially an example of a neutralization reaction as well. But unlike most neutralizations, the key difference here, and we'll show you this in a moment, is that no water is going to be produced. When you react an amine with HCl, what type of product are you going to get? Well, essentially, you're going to get an amine salt. What makes this different from most other neutralizations that you come across is here, you're not going to get water as a byproduct. So one of the things I would suggest, just like we talked about how sodium hydroxide is a strong base, and I would tend to think about it not as NaOH, but as Na plus and OH minus. Hydrochloric acid is a strong acid. So I wouldn't necessarily think about it as HCl. I would think about it as H plus and Cl minus. The nitrogen is going to pick up the proton from the acid. So essentially, the nitrogen picks up a hydrogen. Now, once again, it takes it from 3 bonds to 4 bonds. So the nitrogen is going to have what charge? Positive. What else is present that's going to be attracted to that N plus? It's going to be the Cl minus. Now, one of the reasons why I'm putting the Cl minus on the outside is that, if we, and I know the exams are usually multiple choice or drop down menu, however you want to classify it. But if you had to draw this, I say don't put it in the middle, because then you're almost implying that it's covalently bonded to one of the carbons or the hydrogens. In organic chemistry, when we want to show ionic bonds, we just show the charges of the ions that are present. So you put the chlorine on the outside, and we know that the N plus and the Cl minus are attracted to each other by an ionic bond. So, we usually don't try to squeeze the chlorine in the middle of all that's going on there. But then notice no water. There's sort of no H and OH to sort of talk about. So it makes this a little bit different from most neutralizations because you get a salt, but you don't get any water. One more reaction I see here for us to look at. So let's go to 14.74 B. So here we have an amide plus water plus HCl. And some heat. So what do we got going on here? So amide, water, HCl. What are we talking about here? We're talking about acid hydrolysis of the amide. What's going to be the products? The products are going to be a carboxylic acid and either an ammonium salt or an amine salt. Essentially, the ammonium salt, based on how the textbook sort of limits itself, would just be ammonium chloride, NH4 plus Cl minus. And you'll see that in this example here. And then the amine salt would be like we saw on the previous slide here, an example of an amine salt. Again, whether it's going to be an ammonium salt or an amine salt, the way we're going to come up with the products here is going to be the same. It's just the different types of amides, again, give you different types of nitrogen products. If you start from the primary amide, like we're going to do here, we're going to generate the ammonium chloride, the ammonium salt, as the second product. If we were starting with a secondary or tertiary amide, then we would generate the amine salt as the other product. Okay, couple things. Where does the amide split apart? Between the C double bond O carbon and the nitrogen. The water, I wouldn't think of as H2O. I would think about it as H bonded to OH. And the HCl, I wouldn't think about as HCl. I would think about it as H plus and Cl minus. Here's what happens. The nitrogen picks up two hydrogens, one from the water, the other the proton from the acid. So in this case, the nitrogen goes from NH2 to NH4. Now, it has 4 bonds, so it's going to have a positive charge. And then what else is present that's going to be attracted to it? Cl minus. What type of bond do you have between the nitrogen and the chlorine, the chloride? You have an ionic bond. That's an example of an ammonium salt. The ammonium ion's NH4 plus. This is ammonium chloride. The C double bond O carbon ends up picking up the OH from the water to give us our carboxylic acid. So everything on the left stays the same until I get to the C double bond O carbon. And now the C double bond O carbon is going to be connected to OH. So carboxylic acid plus, in this case, an ammonium salt. I just want to see if we did one with ester and, or we did ester and acid hydrolysis, and we did did we do ester and base? Yes. Okay, good. We did all those. All right. Kim, did you have any questions specific before I do some naming?
No, I don't have any questions.
Okay, no problem. All right, so I think that really covers the gamut of the reactions. All right, so let's take a look at some naming examples. All right, so let's start with 14.58. All right, so here's our first CH3, CH, CH3, CH2, CH2, C double bond O, OH. All right, carboxylic acids. How do we name them? Step 1, find the longest carbon chain that contains the carboxyl group. And that's going to give you the parent or the main chain. You name it by replacing the E of the corresponding alkane name with oic acid. So in this example, the longest carbon chain that contains the carboxyl group is 5. 2 ways of getting it: 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. In this course, they should turn out to be exactly the same, and it definitely is. So a 5-carbon chain, which would give us a parent name of pentane, take out the E and replace it with OIC acid. So the parent name for this compound would be pentanoic acid. Step 2, number the carbons in the main chain, starting with the C double bond O carbon as carbon number 1, which means we have to number the carbons in this chain here from right to left. At the 4 position, what branch do we have? That's a methyl group. And remember, we don't have to give the location of the carboxyl group, because in the open chain form, the C double bond O carbon is always carbon number 1. That's similar to what other functionality we've seen previously. It's very similar to aldehydes. So what do you have here? You have 4-methyl pentanoic acid. Letter B. So for letter B, we have the following. So benzene ring with a carboxyl group attached to it. What's the name of that compound? That compound is what is known as benzoic acid. Just like we saw with phenol and aniline and toluene and benzaldehyde, once we use a parent name of benzoic acid here, which ring carbon has to automatically be carbon number 1? The one that has the carboxyl group attached to it. And notice that in this case, C double bond O carbon is not going to be carbon number 1. Now from there, we would want to number the rest of the ring carbons either clockwise or counterclockwise from there to give the branches the lowest possible numbers. In this case, it doesn't matter which direction you go, because whether you go clockwise or counterclockwise, one chlorine is at carbon 3 and the other chlorine's at carbon 5. So what do you end up with here? you end up with 3,5-dichlorobenzoic acid. Letter C. So for this one, we have the following. So what do you have here? Here you have an ester. Esters are a little bit tricky to name. All right. Essentially, when you name an ester, what you have are two words. The first word is the branch name for the carbon group attached to the alcohol oxygen. So like what? Methyl, ethyl, propyl, isopropyl, the ones that we've sort of seen in this course. The second word is the carboxylate ion name of the corresponding carboxylic acid that could be used to make that ester. Now, how do you name carboxylate ions? Well, essentially, take out the IC acid of the corresponding carboxylic acid name and replace it with ATE. And we'll show you how that comes into play here. So again, when I name an ester, I like to look for that key bond. Key bond is the single bond between the C double bond O carbon, and again, I just like to call it the alcohol oxygen. So again, in this case, the carboxylic acid portion would be to the left of the squiggly line. The alcohol portion would be to the right of the squiggly line. So the first word is the branch name for the carbon group attached to the alcohol oxygen. What do we have attached to the alcohol oxygen here? We have a CH3. What do we call CH3 as a branch? That's a methyl group. For the carboxylic acid, benzene ring with a carboxyl group attached to it would be known as benzoic acid. Take out the IC, take out the acid, and replace it with ATE. So what does benzoic acid become? It becomes benzoate. And therefore, this ester would be known as methyl benzoate. D. All right. Another ester, which is fine. They're a little bit tricky to name. So again, let's find that key bond. The bond between the C double bond O carbon and the alcohol oxygen. Again, we should be able to identify that the carboxylic acid portion is to the left of the squiggly line. The alcohol portion is to the right of the squiggly line. First word is the branch name for the carbon group attached to the alcohol oxygen. So again, we have a methyl group that's present. For the left portion, if that was a carboxylic acid, a 4-carbon carboxylic acid would be known as butanoic acid. Take out the IC, take out the acid, and that becomes butanoate. So that ester would be known as methyl butanoate. And then the last one there is letter E. We've got one more ester. 2, 3, 4. Oh, there's 2 C's. So again, let's find that key bond. Okay. So the bond between the C double bond O carbon and the alcohol oxygen. Again, the alcohol portion is to the right again in this case. The carboxylic acid portion is to the left. So the first word is the branch name for the carbon group attached to the alcohol oxygen. What do you have attached to the alcohol oxygen here? You have CH2 connected to CH3. What do we call that as a branch? That, of course, is called ethyl. So the first word of this ester would be ethyl. Now, for the carboxylic acid portion, 1, 2, 3, 4, 5, a 5-carbon carboxylic acid would give us pentanoic acid. But take out the IC, take out the acid, and pentanoic acid becomes pentanoate. So this ester would be known as ethyl pentanoate. Okay. All right, let's jump to 1472. And here's letter A. We've got CH3, CH2, 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 C double bond O, NH2. All right, so what we have here is a primary amide. How do we name primary amides? What we want to do with primary amides is we want to use the corresponding carboxylic acid name. So in other words, we pretend that the NH2 group is not there. And instead that if it was OH. So if you had CH3, CH2, 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 C double bond O, OH, a 5-carbon carboxylic acid would be known as pentanoic acid. But as we see here, it's not a carboxylic acid, it's an amide. So what's the transformation? Take out the OIC, take out the acid, and replace it with amide. And therefore, this compound would be known as pentanamide. Now, there's no numbers here, but just so you know, because this is actually relevant to B and C, we would number the C double bond O carbon as 1, and then we would number the rest of the carbons essentially in the carboxylic acid portion of the amide. Let's look at letter B. And of course, for letter B, they throw a branch on there that the book doesn't really even discuss, but okay. They do that from time to time. 2, 3, 4. Okay. So here, we're dealing with a tertiary amide. Now, the parent name is the corresponding primary amide name. And what I'm talking about here is not only applies to tertiary amides, but it also applies to secondary amides as well. So in essence, we pretend that the nitrogen doesn't have a carbon group or carbon groups attached to it. We pretend that the nitrogen actually has 2 hydrogens attached to it. So if that's the case, what would be the name of that primary amide? Well, you'd have CH3, C double bond O, NH2. And if we go back to letter A, we would actually treat that as a carboxylic acid. So a 2-carbon carboxylic acid would be known as ethanoic acid. Take out the OIC, take out the acid, and that becomes ethanamide. So the parent name for the compound is going to be methanamide. Now, what about the carbon groups on the nitrogen? The carbon groups on the nitrogen are given by their branch names in front of the parent name each at a location of N. Because remember, as we showed you in the earlier example, when you have an amide and you number the carbons, you're numbering the carbons of the carboxylic acid portion. What about the nitrogen? Because you could have carbon groups on the nitrogen. How do we indicate that you have a carbon group or carbon groups on the nitrogen? They're going to be at a location of N. And just like with branches in general, every branch has to have a location, even if it's the same branch on the same carbon or the same branch on the same nitrogen. Now here, the branches on the nitrogen are different. In the next example, we'll see the nitrogen, the branches are the same. So as we said, and I just erased, the parent name for this amide would be ethanamide. What are the two branches that you have here? The one that you should be aware of is methyl. The one on the top, 4 carbons in a row, is actually known as butyl. And again, I don't know why they give it to you. They don't even talk about a butyl group. So N-butyl and methyl ethanamide. Let's look at letter C. CH3, CH2, C double bond O, and CH3, CH3. All right, so another tertiary amide. So again, we're going to come up with the corresponding primary amide name for the parent name of the structure. So we're going to pretend that instead of the nitrogen having 2 CH3 groups attached to it, we're going to pretend that the nitrogen has 2 hydrogens attached to it. So CH3, CH2, C double bond O, NH2, take that one more step back to the carboxylic acid, CH3, CH2, C double bond O, OH. A 3-carbon carboxylic acid would give us propanoic acid. Take out the OIC, take out the acid, and the parent name for this amide would be propanamide. Now, the 2 carbon groups on the nitrogen are both methyls. So how do we write that properly? N, N, dimethyl propanamide. Both are methyl groups. So of course, we're not going to write methyl-methyl. We're going to write dimethyl. And how do we indicate that both are on the nitrogen? Not just one N, there has to be 2 N's. Every branch has to be accounted for, even if it's the same branch on the same nitrogen. Okay. All right. The time we have left, let's just run through some other examples. Let me just mention a little bit, actually, before I forget, about solubility in water, and especially for carboxylic acids. The ones with 1 to 4 carbons are very soluble in water. Now remember, back from chapter 12, what was the key question that we sort of have to ask ourselves to determine whether a small organic compound is going to be soluble in water or not? If it can hydrogen bond with water. And we talked about that with alcohols, aldehydes, and ketones. For alcohols, we saw that each alcohol molecule can hydrogen bond with 2 water molecules. So they were pretty soluble in water. Aldehydes and ketones, not as much, because they can only hydrogen bond with 1 water molecule per molecule. It turns out that for a carboxylic acid, each molecule can hydrogen bond with 3 water molecules. Let me show you an example. consider ethanoic acid. Remember, carboxylic acid is probably one of the most, if not the most polar type of organic compound that you have, because essentially all 4 atoms of a carboxyl group have charges associated with them. The 3 that are relevant here are the ones on the oxygens, which are both partial negative, and the one on the hydrogen of the carboxyl group, which is partial positive. Now remember, there are other hydrogens in the structure. There's 3 on the carbon, but remember, carbon to hydrogen bonds are not polar, and they are never involved in hydrogen bonding. So the C double bond O oxygen can hydrogen bond with a hydrogen of 1 water molecule, because hydrogens in water have a partial positive charge. The OH oxygen can hydrogen bond with the hydrogen of another water molecule. And then the hydrogen of the carboxyl group can hydrogen bond to an oxygen of another water molecule, because that oxygen has a partial negative charge. Okay. So as seen here, and what turns out to really be the truth, is that each carboxylic acid molecule can hydrogen bond to 3 water molecules. And in the world of solubility in water, it really makes them soluble in water. Probably more, or I would say more than either alcohols, definitely more than aldehydes and ketones. So I did want to mention that a bit. Okay. Let's look at 1468. And here they want us to actually draw a couple structures. So just want to take a look at that. Letter B, triethylamine. So the way I like to draw amines is I like to start with the nitrogen. Now, essentially, because they are derivatives of ammonia, there should be 3 things attached to them. Could be, depending on the type of amine, so not all hydrogen, sorry, that would be ammonia. 1 carbon group, 2 hydrogens, 2 carbon groups, 1 hydrogen, 3 carbon groups, no hydrogens. The key point is that if you only have 1 or 2 carbon groups attached to the nitrogen still has hydrogens attached to it. And the way to think about it is that your starting point is ammonia. So you take those hydrogens off one at a time and replace them with carbon groups. But it's possible, especially for a primary amine or a secondary amine, and it's not probable, it is what it is, that they're still going to have hydrogens attached to them. Triethyl, all 3 hydrogens on the nitrogen are going to be removed, and they're going to be replaced with ethyl groups. How do we draw in the ethyl groups? Well, attached to the nitrogen, we're going to have CH2s, and those CH2s are going to be connected to what? They're going to be connected to CH3s. Let's look at letter C. N, N, dipropyl aniline. So we know what aniline is. For aniline, we have a benzene ring with an NH2 group attached to it. But it's possible that we can take out some of the hydrogens of aniline and replace them with carbon groups. And upon doing so, we can still use a parent name of aniline. Now, how would we indicate that you have carbon groups on the nitrogen and not the ring? Because if we're using a parent name of aniline, the ring carbon with the nitrogen or the NH2 group attached to it would be carbon 1. And then if you had branches on the ring, we would number the ring carbons from there to give the branches the lowest possible numbers. Here's where the locations of N come in again. Because to indicate that carbon groups are on the nitrogen, they're going to be at a location of N. So NN dipropyl tells us that there are 2 propyl groups attached to the nitrogen. Now, what does the propyl group look like? Point of attachment, CH2, CH2, CH3. Point of attachment, CH2, CH2, CH3. So essentially, I've taken out both of the hydrogens of aniline off the nitrogen and replaced them with propyl groups. Letter D. Ethyl, methyl, ammonium, bromide. Now, this name essentially reflects what sometimes I like to refer to as quaternary amines. In terms of an exact definition, you'd want to have 4 carbons on the nitrogen, but it just reflects the fact that when you have 4 bonds on nitrogen, as we saw earlier, the nitrogen is not neutral. The nitrogen is going to have a positive charge. The big difference here in terms of drawing the structure is that we don't want to use ammonia as the starting point. We want to use the ammonium ion as the reference point. Now, in this case, if you look at the name, ethyl, methyl, ammonium, bromide, the ethyl methyl part, that means how many of those hydrogens from the ammonium ion are we taking out? 2 of them. We're taking out 1 of them and replacing it with an ethyl group. We're taking a second one out and we're replacing it with a methyl group. So that starts to shape up like the following. Now, if we take out 2 of those hydrogens, that still leaves the nitrogen with 2 hydrogens left. And the nitrogen is still going to have 4 bonds, so it's going to have a positive charge. Based on the name, what's going to be the anion present so that the overall charge adds to 0, because for a compound, you have to have the overall charge add to 0. Bromide is what ion? Br minus. And again, I wouldn't try to sneak it in the middle of the structure. By showing the charges, you're indicating that there's an ionic bond that's present. So ethyl, methyl, ammonium, bromide. If you just start with a typical amine, like triethylamine, your starting point there would be ammonium. But if you have ammonium, then your starting point is NH4+. The ammonium ion would be the starting point. Let's see if there's anything else. Yeah, so the only thing I think I just want to mention also is like with the carboxylic acid and the base, the other base you could also use would be potassium hydroxide. And just to mention that it wouldn't change anything that we did. The only difference would be that instead of having Na+, you'd have K+. And even for esters and their base hydrolysis, you could also use potassium hydroxide. Again, the only difference would be that is instead of having Na+, you'd have K+. I don't know, I don't think the textbook goes into the amides with using potassium hydroxide. But again, if they did, the only difference would be that instead of having Na+, you'd have K+. It would not change anything else. And that takes us to the end of our session this evening. All right.